Good day, wherever place you are watching from and whatever time you are watching from. This is from CCCSP Futa, Celestial Student Church of Christ Student Parish Futa, and this is from the academic unit. We are having this YouTube tutorial video to explain physics 102. So we're taking physics 102 today. Here is a short notice that this tutorial will be tailored to Futa curriculum according to their textbook and materials. So please do well to listen and follow along. I pray the Lord grant us understanding in Jesus' name. So now let's go to electric field intensity, which some briefly just call electric intensity or electric field. So the electric field intensity is the force experienced per unit charge. Force per unit charge. That is it. So if the formula for charge before is 1/4 pi dot q 1 over q2 whatever r square. So if you divide it by q, so the electric field becomes 1/4 pi dot q over r square or kq over r. So this is the formula for electric field intensity. Now let's leave that. Let's come to electric field lines. So this is a vector quantity. So electric field lines are just lines depicting the movement of your electric current, electric charge. So that is electric field line. And I said it in the last video that this is a positive charge, so it throws off. The negative takes in. You can see the arrow indicating it's a vector quantity, so you can see it has to be direction specified here. So now we'll go to the properties of electric field lines. So here I have the list of some properties of electric field. List is this is not all in the list, you can search as well. The first is they start and end on charges. So they start from positive charge, they terminate on negative charge. So you could have positive, negative. So you go from here, end here, you go from here, end here, go from here, end here, go from here, end here, go from here, end here. So like that. So they go from negative charge and end on. They go from positive charge and end on. They never cross each other. Look at. They can never cross each other. They can never. Density shows strength. If they are much, it shows this is a very strong field. It means probably the magnitude of this is very high, so it shows this is a very strong field. But if it's probably scanty, this is a weak one. Then density, okay, we've gone there. No field lines inside the conductor. Yes, in a conductor there is no field line. Let's assume this is the conductor. It gives out. There is no field line in it. There is no charge in it. The charge inside the conductor is 0, so there is no field line in it. And since there is no field line, they can never form a closed loop. You cannot enter into here. They can't form a closed loop. Now we'll be taking some questions under electric field intensity. So here are two examples, but the first one is a simple one. It's just from electric field lines. What charges are represented below as A and B? So what charge? What you tell me, what is A? What's B? Okay. So now let's see if you are correct. A, B. First off, study the line. It's going out of this. So definitely you should know that is a positive charge. And the same thing to B. They are both positive charge. So they are repelling. Now let's move on. So they will not meet because positive charge is positive charge. They will repel. They have the same reaction going out. Now let's go to the second question, which is get the electric field intensity. So the question would have been simple. It is just 2, because you just go with your formula. Electric field intensity is kq over r square. We have kq over r square to be our formula. Now there is something they want to confuse you with. You see, you only need q. Now to get the e between 1 and 2, you only need, since this is what is joining. You look at this 3 charge. There's only something joining this 3 charge, or there is an intermediary between every of this charge. That is this point Q2. It is between Q1 and Q3. So it means this would be having effect on this, and this would be having effect on it. So you don't need your 2 microcoulomb. You don't need it in the calculation. You only need that, the effect of this on it, and the effect of this on it. So to get your E, should we call it E12? Yes. To get your E12, you only need this charge. It is having an influence on this. Then you need this charge as well in your calculation of E23 to get the influence of this on this. So let's change this to 3 meter to make the calculation a bit easier. So your E12 would be 9 times 10 raised to the power 9 times 4 times 10 raised to the power minus 6 over 3 squared. So your E12 would be 9 cancels 9, you have 4 times 10 raised to the power 9 minus 6 times 3 Newton per coulomb. So this is it, between 0.1 and 2. Now this is positive and this is negative. And according to electric field line, this is different from first calculation. For electric field line, I said it goes from positive to negative. Right? The electric charge enters this way. It goes out of this positive, right? And it enters into, so this is how it moves. Isn't that? So it means positive 4 times 10 raised to the power 3 NC minus 1. That is our E12. That is the effect of 1 on 2, this charge on this. And let's get for the second one, E23. That is, you have your negative. So what is the effect of this on this? And don't forget that electric field enters into negative, goes out of positive, enters into negative. So from both statements, it means it is going this way. Enters into negative or goes out of positive. So this is the direction for E23. Now let's get the value, that's K Q over R squared. And don't forget, we'll only be using this charge here because it is going into here. We said this should be the intermediary of the 2. So between the 2 rather. So E23 is 9 times 10 raised to the power 9 times Q, 3 times 10 raised to the power minus 6. So this is micro. Sometimes you can have nano, sometimes you can have milli and co, so be careful of whatever you are given. So 3 square equals to 9 times 10 raised to the power 9 times 3 times 10 raised to the power minus 6 over 9 E23. So, or you can call it E1, E3, anything, just naming any way you want to name it, E3. So the effect of 3 on this, effect of 1 on this. So E3 should give you, I cancels 9. So you have E3 to be electric field intensity 3 times 10 raised to the power 3 Newton coulomb. So to get your electric field potential at point 2, that is the effect of this on this, the influence of this on this. So how do you get it? This superposition theorem, E1 plus E3. But let's look at the direction. The direction of this one is this way, and the direction of this one is this way. So this is negative, right? So it will be negative 3 times 10 raised to the power 3 because it is this way. Positive, this is where it is standing. What's the contribution of this to this? It goes, it takes in electron from here. From here, it takes in electron because this 2 is positive. It takes in electron. And if this is negative now, it goes this way because it repels electron. Are we there? So it takes in charge rather. It takes in charge. So going this way, positive, then going this way, negative. So you should have 4 times 10 raised to the power 3 plus minus 3 times 10 raised to the power 3. That makes it 1 times 10 raised to the power 3. 15. So this is using the superposition theorem. They are given 2, but if you are given just these 2, we just use KQ over R square of this one alone. But if you are given multiple, we use superposition. Look at which one is in the middle, then the effect of everything around it. We are good to go. So we'll be moving on to electric dipole now. Just a short note on it. Electric dipole, you have 2 equal and opposite charges that are separated by a small distance. When you have 2, they are equal but they are opposite, and they are separated by little distance. For instance, you have plus 2 microcoulomb and minus 2 microcoulomb, so separated by short distance. That's called electric dipole. This application can be found in capacitance and and co. So in capacitors rather. Now, in the textbook, yes, on some PDFs, you might see P equals to Q dot 2D. No, so this 2D is still the distance between them. So what you should be after is what's the distance between them. It might give you the distance between one to the center, to be this one to the center. So definitely D and D will be 2D. So watch out for the question very well. The D they are giving, is it from the center to here? Definitely you know it's 2D for it to be between them. But if the D you are given is between the two of them, there's no need multiplying by 2 again. So be careful of that. Then let's move on to Gauss law. Gauss law states that the total electric flux through a closed surface, when you have a closed surface, the total electric flux you have through it is equal to the total charge enclosed divided by the permittivity of free space. So this is it. The total electric flux you have is equal to the total charge you have divided by permittivity of free space. Then you have this formula which states your electric field density times your area. So this is in case you have areas where there are rough areas that are not flat. So you need to get the sum of your area, then multiply it by your electric field intensity. Or short formula, if you are given the enclosed Q, you divide it by permittivity of. But for a flat surface, the surface where you can determine the area yourself, probably a rectangle, just one area that I can get through formula. Just do what? The E, electric field intensity times that your area. If it is circular face per r square, if it is rectangular, you just do L square. L times B is so that's just the flat surface times the cos theta. If you are given an angle through which the electric field enters, through which the electric charge enters into the field, you put that as well. So and note that Q in a conductor is 0. So there is no flux, there is no, yes, the total electric flux inside the conductor should be 0 because the charge there is 0 in the conductor. So the charge in the conductor is 0. So 0 divided by whatever the permittivity is, that's 0. So we're going to take a question now under this Gauss law. So let's go. So let's take this question and it will be displayed on the screen. The question goes thus: a disk with a radius of a disk with radius 0.10. So radius we have it to be 0.10 meter. Is oriented with its axis, the line through the center perpendicular to the disk surface at an angle of, so we have an angle 30 degrees. Then to the uniform electric field which has the uniform electric field has a magnitude of 2 times 10 per 3 Newton per coulomb. The question goes though that what is the total electric flux? So this is a flat surface because definitely you can get the area. It is a circular, it's a disk. So that's a circular disk. So a circular disk and you are given the radius. So it's not a rough surface where before you get the area you have to do integration to get the area, something like that. So to get this now, the total flux, the question says the total flux. Number one, total flux. To get the total flux, what's your area? The area is pi r square, that's the area of the circle. So you should have 22 over 7 times 0.1 square, right? So our answer should be 0.0314 meters square. Because it's 3.14 times that. Then to get the total flux, you should have EA cos theta, and that is 2 times 10 power 3 times area, which is 0.0314 times cos 30, that is 0.880. So when you do this from your calculator, you should have 63. Then Newton per meter square C minus 1 as your unit for flux. So the second, I hope you get this. EA cos theta. So now we'll be moving to electric potential. Electric potential is the work done per unit charge in bringing a test charge from infinity to a point in that field. So the work you do by bringing a test charge from infinity to a point in that field. So it is given by V equals to the work done, charge. And work done is your force times distance charge. And don't forget your work done is KQ, Q1, Q, R over R square with this your K. So with this is your force, normally R square times your R now over your Q. Q cancels this. So your V is basically QQ over R, and it is a scalar quantity. It's a scalar quantity. Are we good to go? So now let's take an example under this question. If the question is find the potential difference at the point B, given that you have a charge plus 5 microcoulomb at point A. So this is very simple. Your V equals to your KQ over R, and that goes to 9 times 10 to the power 9 times 5 times 10 to the power minus 6 over 2. Then you should have 9 times 5, that should be a 45. But to make things okay, let's use it. 45 times 10 to the power 3 over 2, that gives you 22.5 times 10 to the power 3 volts. So if the question, okay, I know something that will be coming to your mind now is like electric force, like electric field intensity. And we also have more than just a charge in electric potential. And how do we do that? Yes, you can. You still use the superposition theory. Let's assume we have Q1 here, then B, then C. So you have Q2 here. Okay, so your Q1 is your plus 5 microcoulomb. Your Q2 is your next 4 microcoulomb. So what would be your potential difference at point B? So just like electric field intensity, you don't need to charge, you need just a single charge. So you don't need charge on B even if you are given. You just need to get the influence of this on this, the effect of this on this. So we've gotten for AB, I'll call it E1. We've gotten for AB, that or EAB, we've gotten that, and that is 22.5 times 10 to the power 3. Let's call it positive. Then let's get for EBC, which will be KQ1 over R, KQ2 over R. That is 9 times 10 to the power 9 times 4 times 10 to the power minus 6 over 2. The distance as well, 2 meter. Let's call this question number 2. So we have, that will be 18 times 10 to the power 3 volts itself, or Newton per, yes, that will be Newton per coulomb per meter, the English. So EBC. So this as well will be positive, since you have a positive charge there. So okay, I place negative, let me use positive. So if it's positive, it will be positive. So your E at point B, your E total will be 22.5 times 10 to the power 3 plus 18 times 10 to the power 3. So that would give you 40.5 times 10 to the power 3. Hey, why am I using E? V at B. So what if this is negative? So your answer would be a positive 22.5, VAB will be a positive 22.5, and VBC will be a negative 18 times 10 to the power 3. Then you add it together, that is 22.5 minus 18. What if they are both negative? You add them and their final answer will be negative this. So that is minus this, minus value. So minus 40.5 would be old. So let's take another question. What if you have a charge here? Let's say you have a charge here. You have to get potential difference between 2 points A and B due to this charge. So how would you do that? So there is a formula for that. That is V equals to KQ 1 over R1, the distance between here and here, minus 1 over R2. So this is just the formula. The same charge between these two distances. And also, let me remind you that you have E equals to V over D. This is your relationship between your electric field intensity and electric field potential. The difference is just one. While your E is KQ over R squared, your V is KQ over R. So it's basically dividing your, multiplying your E by R or by distance gives you this. So V equals to ED. Z. So now let's take a question in the manual, formal manual. So we'll be taking two questions. The first question goes it says 4 point charges are placed at 4 corners of a square. So this is a square. So question exercises now. 4 point charges. 4 point charges are placed. Q1, Q2, Q3, Q4. So the question says the square is 20 centimeter. So every of these parts will be 20 centimeter. find the potential difference at the center. That is potential difference of this charge on this center, of this to this center, of this to this center, of this, because they all have effect on this center. So what's the potential difference at that center? If the four charges are each plus 2.5 newton, so if this is the first condition, if all four charges are plus 2.5 microcoulomb, so what will be the effect at the center? So what do we need to do? Since every of them have, they are the same, we are using superposition theorem here. Don't forget, what's the effect of u on u, 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 and since they are the same thing, so it means they have the same effect and they would even have the same magnitude. So if this is positive, it means every of them will have positive, because they are the same, they have the same charge and they are from the same distance. So what do you need to do? You just need to get, let's call this point A, what's the r here? So that's the first thing to do. If I have this to be 20 centimeter at this center, this is the center. So what would this be? So this is a triangle. So this is a triangle, and this will be 10 because half of this 10, this as well 20, this will be 10. So I'm looking for this. So this is the center of the circle. So R would be Pythagoras. Using Pythagoras theorem, we have 10 plus 10 square. That's square root of 200, and that is 10 root 2, and that should be 40.14 centimeter. So in meter, the R is 0.14 meter. So it means this is what you are looking for, the potential difference of this Q1 of Q 0.14 meter. So you are looking for the potential difference, that is electric potential. So the electric potential is KQ over R. That is 9 times 10 raised to power 9. 9 times 10 raised to power 9 times, what is our Q, our charge, plus 2.5 times 10 raised to power minus 6 over, what is our distance, is 0.14. Our V should be 5 over 2. So permit me to calculate this using calculator. So you have 9 times 10 raised to power 9 times 2.5 times 10 raised to power minus 3, negative 3, divided by 0.14. So I should have 1.6 times 10 raised to power 1.6 times 10 raised to power 10 raised to power 8. 1.6 times 10 raised to power 8 V. So this is 1, 2, 3, 4, 5, 6, 7, 8. So 1.6 times 10 raised to power 8. So that is potential difference between year to year. So positive, since I have my positive charge here. Now, what will be the effect of this on this two? It will be positive. What will be the effect of this on this two? What will be the effect of this on these two? So it will be positive since they are all the same charges. So using the superposition theorem, we state that you can add up every of the potential difference to get the equivalent. So that is V1 plus V2 plus V3 plus V4. So the effect of this on this V1 positive, effect of this on this positive, V2 positive, V3 positive. So they are the same. So it's basically saying the same value. I'm adding it 4 times. So it is 4 times of V for 1. That is 4 times plus 1.6 times 10 raised to power 8. That is 6.4 times 10 raised to power 8 volts. So the second question says, the second question says, if two of these charges, if two of the charges are positive 2.5 microcoulomb and 2 are negative 2.5 microcoulomb. So if 2 are positive and 2 are negative, so we don't need to take it back and forth again. You can just pick any two of it, that Q1 and Q2 minus 2.5. So their value, we still have the same calculation, but it will be negative 1.6 times 10 raised to power 8 volts. So Q3 and Q4 have positive 1.6 times 10 raised to power 8 volts. So what would happen? So using the superposition theorem, say that you can add everything. So your V equivalent is V1 negative 1.6, minus negative 1.6 minus 1.6, everything times 10 to the power plus 1.6 plus 1.6, everything as times 10 to the power 8. So minus 3.2 plus 3.2, that will be 0. So it is like the positive of this is neutralized by negative of this, positive of this is neutralized by negative of this. So it would be 0. So let's take another question, question number 3 or question number 2 now. That is question 1, but okay, number 3. This is the third question. So also the question says how much work is required to carry an electron. How much work is required to carry an electron from the positive terminal of a 12 volt to a negative terminal? So how much work is needed to carry an electron, that is one electron, from a negative terminal, from a positive terminal of a 12 volt to negative terminal? This is what you should note, that if you are going from positive to negative terminal, that is a negative potential difference. From positive to negative, write it down, is a negative potential difference. But from negative to positive, from bad to good, it means you are increasing. So that is a positive potential difference. So if you want to get this now, your work done equals to QV. The charge is an electron. Electron has 1.6 times 10 to the power minus 19. Then its charge is negative, times your volt will be minus 12 volt, because you are going from positive to negative. As I told you, from positive to negative would be, a negative potential difference. You are decreasing the negative potential difference. So this, at the end of the day, give you positive 16 times 12 gives you what? 16 times 12, what will 16 times 12? 1.98 times 10 to the power minus 18 joules. I've come to the end of potential difference. You can take a lot of questions and as well go through the video again. To cap this series off, let's talk about resistance combination, and capacitance combination. Resistance or resistor opposes the flow of current or electricity or charge. So for resistance, just the combination is what we'll be mentioning. We have the series combination and we have the parallel combination. Series combination is the one you see this way. Sometimes it goes this way. The code is, you see that the right hand of this is joined to the left. See, it's that way. There is no, you can go straight. There is no branching. But in the case of parallel combination, that is where you have this way. So you cannot move to this end on just a single straight line. You have to go. Then you see that there's still a line missed here. So that's a parallel combination. But this one, you can reach this end just on a single line. You can reach this end just on a single line. So for series resistors, what do they have? They share the same current. They have same current. Because the current can move to and fro. It can move from this to the end. So it carries the same current. 2 amperes enters here as well. 2 amperes enters here. It goes enters here, But here, the 2 amperes enters here. Before it comes out, there is something that shares it. It is shared. So here, same current, here they share or split current. So here they share potential difference. Because the potential difference is across both ends, from here to here. So they share it. But here, potential difference is the same thing. So this one, same potential difference. So this one, the resistance increases. This one, the resistance decreases. Decreases in what sense? Is that the formula for the equivalent resistance, that is all these two resistors you have, all these three you have, the equivalent is just gotten by adding them together, R1 plus R2 plus R3. So if you add all this together, definitely you know that you have the resistance. But for this, it is gotten by the reciprocal of 2 plus 1 over R3, like that. But don't forget that when you are solving this, after getting the LCM and solving, you have to cross multiply so that this one will not be the inverse. you can use this quick formula. R equivalent is R1 times R2 over R1 plus R2. This is just for 2 resistors. If it is beyond 2, 3, 4, 5, you have to find the RCM and start doing every of this. Now, in that vein, let's also talk about capacitance a little bit. So, capacitance is just like the opposite capacitance now. In series, capacitance, this is the symbol for capacitance, the unit of which is farad. So this is also series combination, just as I've explained here. And for parallel, it's those. So aside series and parallel combination, you can have a combination of series and parallel together, or join a joint one, but there are still series and parallel. You just bring them together. For instance, after this parallel, I put a series here. It means I have to get the equivalent of this first, then add it to this. It's just like if this is secondary school. So now for this one, they share, they have the same charge. They have the same charge because formula for R is V equals to IR, but for capacitance, Q equals to CV. So we use charge instead of current now. So same charge, the share potential difference, capacitance decreases. Why does it decrease? I would explain. This one, they share the charge, same potential difference, the capacitance increases. So unlike in resistors, the equivalent of capacitance, is interchanged. For series, 1 over C equivalent equals to 1 over C1 plus 1 over C2 plus 1 over C3, like that. And if it is just for 2, it is C1, C2, C1 times C2 over C1 plus C2. For just 2, remember. But for in series, in parallel rather, so the C equivalent is C1 plus C2 plus C3 plus C4, like that. So it increases. But here it decreases because by the time you do the reciprocal, you're going to have a lower value. So this is just the short note on their calculation. When we get to where we would apply them, you'll definitely see. So before then, have a wonderful day. Take care.